Hello, multivariable calculus students. This is Mr. Johnson, and this is the end of section 9.7, and we're going to talk about spherical coordinates. This is the last video of our notes for chapter 9, so congratulations on finishing chapter 9. So with spherical coordinates, we now have three different variables aside from the rectangular coordinates that we're dealing with. So instead of x, y, and z, we have this little letter that looks like a P. It's called rho. And then we have theta, which we've been used to. And then we have another angle now, a second angle that's called phi. So we have theta really positioned in the same spot that we're used to. So it's going to be off of the positive x-axis. We have rho, which is the distance from the pole out to the point. So remember that r is this distance right here. That's r. Rho is sort of similar, but there is that difference that it comes off of the origin and goes straight to the point. And then we have this second angle that we have not used yet, phi, and that's going to be angle off of the positive z-axis. So I'm going to show you where our equations come from and how to sort of digest what's going on. So again, what I had mentioned was that this length right here is r. The same length is actually going to be projected up here to the z-axis. And so this is also r. What I'm going to do is I'm going to show you what the equation for r is and ultimately the equation for z, just really quickly. So if we have phi, this angle here, and we have rho, which is our hypotenuse of this little triangle that I just formed here, then we could do a right triangle trig. Again, what I'm doing is I'm taking a look at just this green right triangle, okay? And our right triangle trig says that we could take the cosine of that angle, phi, and it's equal to the z value, again, which is right here, just whatever the z value is, divided by rho. And if we were to solve for z, we get rho times cosine of phi. And that is one of the equations that we want for spherical coordinates. Okay, so that's an important one. The other way that we could do this is we could take sine of phi, and if we do that, we get, let's see, we get r divided by rho, which gives us r equal to rho times sine of phi. Now this one's not important really for us to memorize just because r is not part of spherical coordinates, so we don't really have to convert to r. But one of the things I want to show you here is that we have our equations from cylindrical coordinates. So for x and for y, and our equations for x and y in cylindrical coordinates are polar coordinates, we can now convert to spherical coordinates by just substituting in r. So these equations now become x equal to rho sine of phi cosine theta, and y equal to rho sine of phi and sine of theta. And these are two that we obviously need to memorize here. There's one more that we can now memorize as well, and that is that we have rho squared equal to x squared plus y squared plus z squared. So there are really four equations here that we want to keep in mind. And also we want to make sure that we understand the restrictions of rho. Rho is going to be positive, and phi is going to be 0 to pi. You can also add in that theta is anywhere from 0 to 2 pi. Okay? All right, let's talk a little bit about some of the graphs that come out of spherical coordinates. So if you were to have, for instance, rho equal to a constant, you had, let's say, rho equal to 2. That means that rho is always 2, and theta could be anything 0 to 2 pi, and phi could be anything 0 to pi. That actually gives you a sphere. You could have the angle theta equal to a number. Let's say it's theta equals pi. You will have a half plane because the rho value is going to be any value that is positive greater than or equal to 0, and phi is going to be from 0 to pi, which causes you to have any point along this half plane. And then let's say that you have phi equal to a number, you will have a half cone because your rho can be anything and your theta can be anything, but if phi is stuck at a certain value, let's say it's pi over 4, then you'll have a half cone. All right, here is a little diagram that shows the relationship of all the different things that we've talked about in this particular section, so you can use that as a reference. I mentioned a lot of those things already when I introduced the formulas. You can also see the formulas below, and again, you just need to know these 4 formulas. Keep in mind that it is not universal, the relationship of the angles. So you can see the little note there that in some physics books, the angles are actually swapped, and instead of rho, they actually use r. So depending on if you use this again later in either mathematics or science, it may be a little bit confusing because there isn't an agreement universally that these variables represent what I've just shown you. In most multivariable calculus textbooks, this is the case, but there are some that don't, and then there are, of course, some science books that are a little different as well. Okay, let's move on to the next page. All right, let's try 3 examples. So the first one is that we're going to plot the point, and again, I'm not too concerned about how accurate this actually is. I just want you to get an idea of where you're trying to move the angles and where this point should be. Try to be as accurate as you can, obviously. But what we have is an angle of pi over 4 on the x, y plane. So this is pi over 4. And we have then an angle of pi over 3 off of the z axes. So let's say that, I don't know, let's say this is pi over 3. So maybe it looks like this or something. And then the rho value is going to be 2. And if you sort of are projecting this point up, there's your point, let's just call it point P. So that's how all of the variables work. It's really important to keep in mind these variables and where they are in the ordered triple here, just because you want to make sure that you don't mix up, especially the angles and which ones they are, because that will just change your values. So we're going to look at this point then in rectangular coordinates. So one of the things we can do is just start with our equations for x, y, and z, and we have 2 sine of phi and cosine of theta. And that gives us 2 times sine of pi over 3 is going to be the square root of 3 over 2. And cosine of pi over 4 is square root of 2 over 2. And that simplifies the square root of 6 over 2. And then what we'll have is for y, 2 sine of pi over 3 and sine of pi over 4. And remember, sine and cosine of pi over 4 are the same thing. So we actually happen to get the exact same value for y. And then for z, we have 2 cosine of phi, and that will give us 2 times 1/2, which is just 1. So our point in rectangular form is square root of 6 over 2, square root of 6 over 2, and then 1. Okay, for example 5, we're going to go the other direction, and really this point should be specified. This is going to be a point in rectangular form. So what we're doing is we're going from Cartesian or rectangular form back to spherical coordinates. So we have x, y, and z. So one of the things we could do to start with is use our equation for rho squared, which is x squared plus y squared plus z squared. So we have 0 squared, we have 2 root 3 squared plus -2 squared, and then that's going to give us 4 times 3. So we're going to get 12 plus 4, which is 16. So that would tell us that rho is 4, since it has to be greater than or equal to 0. And then in terms of finding the first angle, what I would do is use z, because it has one angle. So we have z equal to rho, which we now know is 4 cosine of phi. And since z is -2, this gives us -1/2 equal the cosine of phi. Now remember, with your angle for phi, it's between 0 and pi. So if cosine of that angle is negative and it's 1/2, then the only angle phi that we could have is 2 pi over 3. And then we want to find theta. So for theta, you could use kind of anything. I guess I'm going to use x just because it's 0, so it's going to be easier. So x is equal to rho, which is 4, times sine of phi, which is 2 pi over 3 times cosine of theta, which we're trying to find. Now, because I chose the one that was equal to 0, it ends up setting it up nicely in an algebraic sense. Our angle theta will simply be pi over 2. And remember, theta can be anywhere from 0 to 2 pi. But then what we want to do is kind of think about where this point is originally using rectangular coordinates. So if we have our x, y, and z axes, this particular point, remember, is 0 on the x. It's 2 pi over 3 on the y, wherever that may be. But then for z, it's negative 2. So it's it's down here like that, which means that if we envision what's happening to theta, we want to make sure that we allow our axis using spherical coordinates to find that point accurately, which means that we need this angle. This angle should make sense. Pi over 2 brings us to the y-axis, and then phi is 2 pi over 3, which means it brings us all the way down there, and then we come off of the origin using the distance of rho to get to that point. So anyway, we want to kind of think through, does it make sense to work through all of those angles and that distance? Okay, keep in mind that you have to have theta and then phi, and rho comes first. So there's your point in spherical coordinates. Okay, let's try our last example. Find a rectangular equation for the surface whose spherical coordinates is given by that equation. So we have rho equal to sine of theta sine of phi. I'm going to multiply both sides by rho. So I'm going to get rho squared equal to rho times sine of theta times sine of phi. Rho squared is the same thing as x squared plus y squared plus z squared. And rho times sine of theta times sine of phi is the same thing as y. Now this looks kind of like a sphere. We want to arrange this a little bit differently. So we have x squared plus y squared minus y plus z squared equal to 0. I'm going to complete the square for y. So we have y squared minus y plus 1/4 plus z squared equal to, I'm going to balance it, so 1/4. That ends up giving us x squared plus the quantity y minus 1/2 squared plus z squared equal to 1/4. So this is a sphere with a center of 0, 1/2, and 0. And then the radius is the square root of 1/4, which is 1/2. Okay, that does it for section 9.7. Thank you.